Okay, thank you.
All right, excellent. Hi, everyone, and welcome to our workshop on monoidal and two categories in representation theory and categorification. And thank you to everyone for either waking up very early or staying up later, depending on your time zone, to join us today. And of course, thank you to the speakers. So today, for our first talk, we will be having Raphael Rouquier from UCLA, who's going to tell us about affinization and modular representations of finite groups. Just as a quick note, before I let Raphael take the floor away, we'll be having a little 5-minute break at the 25-30-minute mark. So if you have any questions, feel free to ask then. And in between the talks, just please type your question into the chat and I'll keep an eye on it. And Raphael, hopefully it's okay if I interrupt you every now and then with a question from the chat.
Yes, please. Thank you.
All right, excellent. Please, Raphael, take it away.
Okay, thank you very much, Nicole, and thank you for the invitation. So I'd like to discuss somehow two topics. One has to do with abstract search for categorification and higher representations. And another has to do with trying to solve questions about modular representations of finite groups of Lie type. So that's the two parts in the title. The first part, affinization, has to do with affinizing Kac-Moody algebras, and the second part is about finite groups of Lie type. Or maybe more general finite groups, and I will start indeed with not with Lie type, but with the symmetry group. And so, if you look at representations of the symmetry group in characteristic P, and not just a single symmetry group Sn, but you put all symmetry groups together, and you can induce from symmetry group Sn to Sn plus 1. And you take all those functors together, so you have this E, which starting from some representation of some Sn will give you a representation of Sn plus 1. So we view that as an endo-functor of this big abelian category A, where we put together all representations of all symmetry groups. So this has been done, and it's a very useful thing for symmetry group, for studying representations of symmetry groups. So what has been also very useful is the use of Jussius-Murphy elements. So we'll use them, so this capital X. So first we start with the symmetry group Sn plus 1. And in its group algebra, we consider the sum of transpositions involving n plus 1. So if we right multiply by that element, that element commutes with the action of Sn, with elements of Sn, that's the whole point. So if you right multiply by that element on Sn plus 1, this is going to commute with the right multiplication by Sn, and also, of course, the left multiplication by Sn plus 1. And the induction functor from Sn to Sn plus 1 is given by tensoring by that bimodule. So this X defined n by n. If we take the sum of all of those, we end up with an endomorphism of E. Okay, so we can now do the same thing with the restriction. And if you do, so it's going to be left and right adjoint to E. So this map X gives an interesting structure to the endomorphism ring of E to the n. So applying E to the n will be like applying n times our induction functor. And so we do, when we do that, we can break E to the n as various ways, as E to the maybe n minus I times E to the I minus 1. So we do successive inductions. And we have this endomorphism X of E. So we can apply it when we take the power of E at any location. That gives us an endomorphism Xi of E to the n. And there's something that's more sorry, maybe more obvious. That's an endomorphism coming from the symmetry group itself. So if you induce not just one step, but two steps, say from Sn to Sn plus 2, then in the group algebra of Sn plus 2, you can multiply by the transposition n plus 1, n plus 2 on the right, and that's commuting with our actions. So that's what I call small s in the description here. So small si is an endomorphism of e to the n, which is applying a certain transposition somewhere. We write e to the n, and we put select an e square inside. And those small si and xi's, so the small si's will give, they will satisfy, they will generate a symmetry group. They satisfy the defining relations of the symmetry groups. The xi's commute, and si and xj's don't quite commute. And we get these degenerate finite algebra relations. Okay, so that's again a classic topic. So what gets interesting is that you can use x to break down the functor e. So the functor e, or these bimodules, they have an endomorphism. So you can decompose into a direct sum of generalized eigenspaces. It turns out the eigenvalues of x are indeed in Fp. And we can take ER to be this generalized R eigenspace, for R is an element of Fp. And we can decompose similarly F, with Fr being the adjoint to ER. So now on our abelian category, somehow we start with E, and we take F and adjoint as the adjoint. And the fact that we have this X acting on E allows us to break down E as a direct sum of various functors. And so we have now all those functors, EIs and FIs, acting on our abelian category. And if we pass to the Grothendieck group, if we look at characters or classes in K0, these EIs and FIs, which are exact functors, exact endofunctors of A, they are going to give linear endomorphisms of the Grothendieck group, maybe the complexified Grothendieck group, and they are, these ERs and FRs, they satisfy the defining relations of an affine algebra, or its enveloping algebra. So the affine algebra of type AP minus 1 hat, this affine algebra SLP hat. So that's something with Chong we called two representation, or I don't know if we call it like that, but that's something we studied, and you can study more generally abelian categories endowed with that type of structure. And like you would classify, I mean, you can do that for SL2 or for SLN or various type A affine algebras. And if you put some integrability conditions, you will have a theory like that for finite dimensional complex and simple algebras, or analogs for Kac-Moody algebras. So you have some sort of classification of abelian categories, of minimal ones corresponding to simple representations, and you have a Jordan-Hölder series for more general abelian categories. So that's something that you can do in a general framework. So you can forget about symmetry groups, look at general abelian categories, and you can answer problems about, we could answer a problem about the specific abelian category involving representations of symmetry groups by somehow recasting the problem into the more general framework, eventually of representations, two representations of SL2. And we could solve that problem by somehow reducing the problem to the case of a simple representation of SL2. So if you think of SL2C, its simple representations are not very complicated, just symmetric powers of the two-dimensional vector representation. And once you categorify, it's not too complicated either. We could analyze those explicitly, those representations, and get what we wanted was some sort of analog of the adjoint action of the Val group on representations. And we could check that on simple two representations. So if you want to generalize the theory from type A, SLN, SLN hat, SLP hat to other types, you need to change a little bit the X and the S size, and you need to do a very simple change of variable. And then that in turn generalizes to arbitrary Kac-Moody algebras. So that's something that was done independently by Kovanov and Lauda. And that relies on the notion of quiver-Haker algebras. So you can define, so what's implicit in the construction I explained above is that, say if you look only at the EIs, these endofunctors, really, they come from the action of a certain monoidal category. So in the Kac-Moody setting, you will have generators EIs, I is running over, say, the nodes of your linking diagram. Each EI is coming with an endomorphism X. And now we have maps from a product EIEJ to a product EJEI, and this satisfies certain relations. And the quiver-Haker algebra itself is the endomorphism algebra for a certain object in this category, very much in the way that we obtain the degenerate affine Haker algebra above by taking the endomorphism of E to the N. Right, so there's one thing I mean, you have to check that indeed the two definitions are the same. So you need to check that, say, for SLP hat, the quiver-Haker algebras are the same as degenerate affine Haker algebra, or you'd use affine Haker algebra in the theory of this Chang in characteristic 0. And something you can check, so up to some sort of completion or localization, quiver-Haker algebras for SLP hat agree with degenerate affine Haker algebra, and this has a consequence that the symmetry group, the group algebra of the symmetry group itself can be realized as a certain quotient, a cyclotomic quiver-Haker algebra. So that's something that was considered independently by Bondan and Klechev. And that's something that an extension of that will be discussed next by Chris Baumann. And these are really this is rather striking because these are explicit isomorphisms. So it's in this specific case I wrote, it's very much like isomorphisms that were constructed by Cherenik, Drinfeld, and Lustig involving affine and degenerate affine Haker algebras. So you have relatively simple explicit isomorphisms. And one thing, for example, that you can use, that these quiver-Haker algebras are graded. So you get some gradings on group algebras of symmetry groups, and that gives you some version of Q decomposition numbers, which if you say if P is big enough, or maybe if you do the similar construction for Haker algebras of roots of unity, so you really are in characteristic 0, you can show that these Q decomposition numbers have to do with canonical bases in certain representation of quantum affine algebra or quantum Kac-Moody algebra. Okay, so this interpretation brings also naturally some version of Q decomposition numbers. Right, so check there. So what I will be doing now is moving from the symmetry group to the general linear group of a finite field. So the theory is very similar, and that's something we also discussed with Schlong, and we have exactly the same type of structure. It's just that the group algebra of even the blocks of the general linear groups are bigger. So let me explain that. So representations of general linear groups over finite fields can be broken into, can be partitioned into so-called Lustig series. Very much like if you have a matrix, an invertible matrix, you can write it as a product of a semi-simple matrix, so a diagonalizable matrix times a unipotent matrix. both of which commute. So similarly, you can describe describe representations of finite group of Lie type, here GLNQ, by saying, well, I'll partition according to semi-simple elements, so that would be of the dual group, and then for each semi-simple element, you'll be considering so-called unipotent representations of the centralizer, which is a complicated to define geometrical notion, except for GLN, where you have, as I'll show you, you have a simple description. So we're looking at representation modulo L of GLNFQ when L does not divide Q. Okay, so it could be characteristic 0 when it's semi-simple, but we're not looking at L dividing Q. So now, when you look at representations of finite groups of Lie type, you first consider so-called principal series representations. So that involves fixing a Borel subgroup. So here we take upper triangular matrices, and we take the trivial module induced from the Borel to the group. So this permutation module has an endomorphism ring that has been well studied. That's a Hausdorff algebra of the symmetry group, for which the parameter is the parameter Q is really or Q here is really a prime power. So taking homomorphisms from this induced module defines a functor from a category of KG modules from representations of GLNQ to modules of the Hausdorff algebra. And so the KG modules, this category breaks into many blocks. And this functor taking Borel fixed points factors through a certain sum of blocks, which I call KG uni. So it's more the unipotent part of the category of representation. So every representation will break down as a direct sum of a unipotent representation and a non-unipotent one, and we're looking at that part. And the other parts can be somehow can be recovered from the unipotent part using certain Morita equivalences. Okay, so the Hausdorff algebra is going to tell us a bit about representations of GLNQ, but we classically, after say deeper gems, one should use a little more, and that's the Q-Schur algebra. So, so the Q-Schur algebra goes, is originally defined as a quantization of the Schur algebra. So if you take the vector representation of GLNQ or GLN, and you take a tensor power of it, its endomorphism ring for the action of the general linear group is going to be a quotient of the group algebra of the symmetry group, and there's a double centralizer theorem. If you take endomorphisms of a tensor power commuting with the action of the symmetry group, this endomorphism ring is generated by the action of the general linear group. And this action defines a certain quotient of the group algebra, which is Schur algebra, or here we're doing the FQ version, so it's a Q-Schur algebra. Okay, so this Q-Schur algebra, Sn of Q, is a quotient of the group algebra of the GLNQ, acting on tensor space. So we take defining representation. Well, anyway, it's not exactly like that in this characteristic L. Really, what we should say is instead we take this induced module from B to G of the trivial representation. That module is not this tensor space for the Hausdorff algebra. It's just a different module, but it differs only by multiplicities. So if you decompose your tensor space as a module for the Hausdorff algebra, or you decompose this induced module from B to G of the trivial representation for the Hausdorff algebra, you will find the exact same indecomposable summons. It's only the multiplicities are going to change. And in particular, since you have two modules which have the same indecomposable summons, just different multiplicities, their endomorphism rings are Morita equivalent as the same module categories. So if we look at this green square, it tells us that this the modular category of the Q-show algebra, which is equivalent to the modular category of a quotient of Kg, this Kg bar, by pulling back that gives rise to Kg module. So we can view the category of modules over the Q-show algebra as a subcategory of the category of modules for the general linear groups, general linear group. And we have this square underlined in blue with which is a commutative diagram. All right, so now we can find all irreducible, all simple modules, all the unipotent ones for general linear group. We can find them in this subcategory, Sn of Q mod. The simple modules for Q-show algebras are parameterized by partitions of n. It doesn't depend on the field, on the characteristic, 0 or L. And so you have a characteristic 0 version of your simple modules, say for GLN, and characteristic L. And you can look at the decomposition matrix. You can think of LC of lambda maybe as some version of Specht module or Verma module or bimodule. And so you can look at those multiplicities, and this is given exactly by the decomposition matrix of a Q-show algebra, the characteristic L. And if L is big enough, it's going to be the same as the decomposition matrix for Q-show algebra in characteristic 0 when you go to a D root of unity. So D now is the order of Q, multiplicative order modulo L. So let me give a diagram which is simpler for GLN, but I want to give a diagram of the decomposition matrix for general finite group of Lie type. So for general finite group of Lie type, there are more unipotent representations. So if you look at characteristic 0 representations that are part of this unipotent chunk of the category, there are those which are so-called principal series, which come from the Hausdorff algebra, but there are more. So it's this bigger green box. So for GLN, principal series and unipotent part are the same, and so the blue box is the same as a green box. And so in general, so you do have less, and there are further rows in the decomposition matrix. The green part is square, the blue part is square, but there's more. And there's a smaller, even smaller part with fewer columns, which is the decomposition matrix of the Hausdorff algebra. So the columns are parameterized in our case, for example, by D regular partitions of n. And for GLN, the rows, except for the black part, will be parameterized by partitions. So this blue and green matrices that coincide for GLN, rows and columns parameterized by partitions of n. And the black part, the columns are parameterized by D regular partitions of n. And on top of that, you have this non-unipotent chunk of the decomposition matrix. So the green part of the decomposition matrix, for say for GLN, or the blue part, everything, all of that depends only really on D, or at least conjecturally. Maybe yeah, it's true if L is big enough. So it doesn't depend on Q, but the number, this non-unipotent part, the number of rows there does depend on Q. So it will grow as a larger and larger power of L divides Q to the D minus 1. Q to the D is 1 mod L, and the larger the power of L divides Q to the D minus 1, the more you will have of those non-unipotent rows in your decomposition matrix. Okay, so for GLN Q-show algebras have given a good approach to decomposition matrices. In particular, in that they have given us some things that somehow where the dependence in Q could go away. I mean, you look at the Q-show algebra. Okay, well, if you take it modulo L, Q is an L root of unity. So it just what you're given is just n and this D. You take your Q-show algebra to D root of unity, and if L is big enough, you can even leave that in characteristic 0. So people have tried to do that for something similar for other finite groups of Lie type. But it's turned out that this green part of the decomposition matrix doesn't seem to come from any nice algebra, like a Q-Show algebra, that is, in general. Specific cases, it works, but even for classical groups, it doesn't seem to be a good analog of Q-Show algebras. So what I'll discuss is, a way to fix that. And first, some of the first case one probably typically would want to deal with after GLN, Q is our unitary group. So there is a version of unitary groups over finite fields where instead of taking n by n matrices of FQ bar, which have the properties that their coefficient raised to the q are invariant under raising to the q's power. So now you look at matrices such that if you take the transpose inverse of that matrix raised to the q's power, you get your matrix back. Okay. So it's a bit like doing a unitary group of complex numbers or real numbers and replacing complex conjugation by this raising to the q's power, by the Frobenius homomorphism. So these are finite groups, and they're part of the, they're almost simple, and they're part of the class, of the list of finite simple groups. And you can play the same game. You have a Borel subgroup, but now the Borel subgroup somehow is when you induce the trivial representation from the Borel subgroup, you get fewer characters than you would for GLN, and the homomorphism ring is not of type A, it's type B. So you have to take your Hausdorff algebra of the symmetry group, and so you have to fold according to the diagram automorphism of type F A n minus 1, and you get this Hausdorff algebra of type B of n over 2. And so the irreducible unipotent representation of the unitary group, you can write it somehow as a GLN of minus q, whatever it means. They are still parameterized by partitions of n, but those of the of a type B Hausdorff algebra, they will be parameterized only by partitions of n with an empty 2 core. So in this induced representation, you will find only very specific simple modules as quotients. Only those corresponding to empty partitions of n, empty partitions of n which have an empty 2 core. And so it's been a problem to find decomposition matrices for unitary groups. So for general linear groups, you can rely on Q-Show algebras, and then you can either use Lascaux-Leclerc-Thibon or Lustig's conjecture. And when L is big enough, it's going to be given by specific combinatorial objects. So for unitary groups, that was missing. And with Olivier Dudas discussing in our joint work, we've come up with a conjecture for those decomposition matrices. So I put L bigger than n there, but I should have put L. Maybe I should fix that later. Maybe I should say, oops. Black for that. Maybe it's, oops. Choose a black, yes. So let's say L big. Okay. So what's striking is that we end up having to come up with a two variable version of decomposition numbers. So the typical Q decomposition numbers, when you specialize Q to 1, you get your decomposition numbers back. So here we have two variable decomposition numbers, which when specialized to, when you specialize both variables to 1, give decomposition numbers. So I've given the I've stated the conjecture in a particular case for an L divides Q plus 1, And this involves combinatorics, only combinatorics of Macdonald polynomials. And oops, maybe I'll just before the break say a couple more things. So we've been able to check that the conjecture holds up to n equals 9 using these calculations made recently by Gunther Mahler and Olivier Dudas. And for example, the matrix for n equals 3, the one I've indicated, the unipotent part of the decomposition matrix, which was green in the decomposition matrix before. And that's, for example, involves a coefficient that involves a negative sign. So you have a coefficient q minus t that will go to 0 when specialized. And so that's work for other Ds, and it involves some basis in certain Fock spaces. And so let me finish with just one more complicated example. So when n equals 8, so you can make the calculation of the decomposition number that will be the one in the bottom left, which is known to be 0. But the polynomial, when you apply this combinatorial machinery, the polynomial in Q and T you find is not 0. There are lots of cancellations. So these QT decomposition numbers are not usual ones measuring having to do with grading or maybe by grading and refining things. It's something different. So I'll be discussing that and explaining why it has to do with affinization of SLP hat, or affinization of the kind of categorification one normally encounters. Okay, so we're taking a break now.
Yep. Thanks, Raphael. And so let's take a 5-minute break. So we'll be back 5 minutes from now. Everyone is, of course, welcome to take a break except for Raphael. He is stuck here with us. So if anybody has any questions, this is a good spot to ask away. Actually, Raphael, there's a question in the chat.
Yes,
so Monica Vazarani asks, is it still 0 if you set Q equal to T?
Okay, so there's 5 minutes to check this big polynomial. She says Q equals T. Let me try to think.
I guess Olivier answered that not always, but can you be more specific about this?
I don't see a reason why that's for sure. I mean, we don't have a oops, I've lost my is it back on? No. So no, it's not what I want to do. So yes, we in this example, I don't remember. I think we did check that at some point. I don't remember. Sorry, but it's not something we have so far we have no expectation whatsoever about signs and cancellations and things like that. Okay, is my screen coming back or?
Yes, it's returned.
So we just don't know, and we are very confused about. So far, we don't understand these types of properties.
And then Arun Ram is asking if you can give us some indication of how to build DQT for Macdonald polynomials.
Yes, so it's not very complicated. You can, if you take your space of symmetric functions and you add the variable say Q and T. On that space, there is what's it, Garcia's nabla operator. So it's diagonal on Macdonald polynomials.
Mm-hmm.
Macdonald polynomials are parameterized by partitions by partitions, and on a given partition, it's going to return. So Macdonald polynomial is sent to a power of Q times and a power of T, which depend on the small a of lambda or small a of, n of lambda or n of the transpose of lambda. And this matrix dn of qt is obtained by by factoring this matrix nabla. So here you take the basis. So you take not quite the symmetric functions, but you take platisms of symmetric functions. Mm-hmm. So let me maybe try to give you a precise formula that in my notes. Maybe put that. So there is this quick way to. Okay, so what do we look? We look at platisms. We take S lambda and we take a platism with respect to T. So what do you is it called 1 minus T? So we take a platism. And in this basis, we write nabla as a product of a matrix Dn of the T inverse certain diagonal matrix times Dn TQ. I mean, I wrote the matrix is QT, and here I'm saying TQ, it doesn't matter. But the so we can uniquely factor this. You can uniquely factor this matrix nabla and this basis of Schur function to which you have applied a platism. You can write it uniquely as a product of a triangular matrix, a diagonal matrix, a triangular matrix that formed by putting some conditions on the coefficients of that triangular matrix dn qt or dn tq. Okay, so that's how we define these matrices. So they have to do really with dividing by 2, somehow cutting in 2 pieces the nabla operator.
That's great, thank you. And that's actually perfectly on time to start the second half of the talk. So if you can take it away, we'll have more time for questions afterwards, of course, everyone.
Okay, is it going back? Yes. Right. So, wait, what's going on? Okay, sorry, I have. Wait, what did I do? Sorry, give me a second. I think I did something wrong with my. Sorry. Let me stop the broadcasting. I think I did something. I think I didn't edit the right thing. So 1 second. I did something wrong with the file, with my PDF file, I think. Yes. Okay. So let me explain. So what I'd like to explain is why do we go from 1 variable decomposition numbers to 2 variable decomposition numbers? Okay. So this is part of so 1 variable decomposition numbers. So this has to do with somewhere with an action of quantum, the quantum group of type of a certain affine Lie algebra, SL D hat maybe here. And we see also some quantum action or something like that should be happening for what I've described before, involving two variables, and this involves a toroidal Lie algebra, and it's two variable quantum group. So somewhere we've gone from an affine Lie algebra to toroidal Lie algebra. We have affinized our affine Lie algebra. And so typically affinization arises as by specialization or maybe degeneration, like going from characteristic 0 to characteristic P. So you can think of going from geometrically that you have gone from ZP to mod P. Instead of being at the generic point, characteristic 0, you do mod P, you've specialized. And somehow by specializing, you have introduced, you've removed certain constraints and there are more symmetries. So we see that typically in representations of complex semi-simple algebras where we see the Weil group. In controlling representation theory, if you do something similar in characteristic P, you find the affine Weil group controlling the representation theory. So going mod P is going to increase symmetries, and so what's going on here is that we are already in characteristic L, so we can't go more modular, but there's something else we can do. It's to make Q to the D minus 1. So instead of say going, making Q to the D minus 1 closer and closer to say to 0 modulo L. So Q to the D closer and closer to 1 mod L. If you want the L-adic valuation of Q to the D minus 1 going to infinity. So there's a way to make sense of that. And that's how you end up with this toroidal algebra, and it's two variable quantum version. So it's something one can define in a roundabout way. For D equals 1, we've been able to do more satisfactory things, and you can view the this category of representation we're discussing, representations of GLN Q modulo L. So now L divides Q minus 1. Q is a 1 mod L. From the point of view of the Hausdorff algebra, it's not very exciting, but from the it's semi-simple if L is big enough. Similarly, but it's not like that for GLN. It's not semi-simple. The composition matrix is a bit boring. So we can you can view this abelian category as having to do with the deformation of a certain geometrical object. So you take a two-dimensional affine space, and you look at families of n points. So you can make a variety out of that. That's a symmetric power. Sn of A2, families of n points. So that's going to be singular as soon as n is 2 or more. And there is a very nice way to desingularize that. It's called the Hilbert scheme of points. So instead of looking at families of n points on a two-dimensional affine space, you look at their defining ideal. So you have a polynomial ring K of xy, and you look at ideals which have codimension n. And now you take that, you take the moduli space of those ideals. And what this is going to parameterize is not just families of some of n points, but it's going to really parameterize zero-dimensional subschemes of A2 whose coordinate ring with global functions is an n-dimensional vector space. And that's a smooth variety. So this variety, you can look at its coherent sheaves. There are if you do something a little bit, there's a causal duality involved. So if you do something a little bit derived, you have to say, well, I'm using a grading. There are gradings because on a two-dimensional vector space, you have a two-dimensional torus acting. And one of the directions you choose, you have an action of a multiplicative group, and you have a grading, and you can look, instead of looking at complexes of sheaves, you look at differential graded sheaves with this grading. So there's small things there, but you can forget about that and take the derived category. And there, I mean, this has to, when you look at coherent sheaves, I mean, this you find infinite dimensional home spaces, etc. So it doesn't look at all like a representation category, but you can find a different T structure there whose heart has a deformation giving you representations of GLN. Okay. So going the other way around, somehow you're starting from some algebras that controls representations of GLNQ, unipotent ones, and you can there's a you can think of it as having a parameter, and you're looking maybe at the parameter value 1, and when you take the parameter value 0, what you find is something which is like coherent sheaves on Hilbert scheme. And for the unitary group, we expect something like that to be true. That on that category of coherent sheaves on Hilbert schemes, there is another T structure which we can specify, and we can also specify the deformation, but we don't know how to relate it to the unitary group. So the appearance of Macdonald polynomial, Macdonald theory comes exactly from the fact that we've been looking at these Hilbert schemes, and that's so Hyman's theory. The Macdonald polynomials correspond to skyscraper sheaves at torus fixed points on the Hilbert scheme. And the Nabla operator corresponds to transferring by O of 1 on the Hilbert scheme. So that's all part of somehow the reason why we expect that if this conjecture about the deformation of the T structure is true, then it should be true that the decomposition matrices for unitary groups are given by those by specialization of certain two-variable polynomials. So I've talked of the theory for D equals 1. Otherwise it would involve other Hilbert schemes. So in D equals 1, there's something else you can do. You can play somehow with D in a different way, and that's also related to T structures. And that's a theory of Bezos-Kamnikov relating to a theory of Maulik and Okunkov of stable bases. So this is somehow, what we're doing is somehow orthogonal to their theories, but it's probably part of some general combinatorial constructions you can do. So here it's D equals 1. So we're really looking at GL1, but the toroidal GL1. And the toroidal GL1 has a very big, somehow Weil group, whatever it is, a very big Breit group. Okay, so it's a huge amount of symmetries, and that's responsible for the type of combinatorics one finds. And one can also, without geometry, so here we're relying on Hilbert schemes and Hyman's interpretations, you can also define some sort of Macdonald polynomials, Nabla operators, and these matrices Dn of Qt for other finite groups of theta, And the number of calculations seem to match with the non-decomposition matrices. So what happened is that by taking this limit, by degenerating GL and Q, we're dealing with Hilbert schemes in characteristic L. So going from characteristic L to characteristic 0, relating the two, is the idea that when L is big enough, things are going to stabilize, and it's going to be the same as in characteristic 0. And so the other part is the first blue arrow is that for finite groups of theta, GLN, or maybe unitary groups, or etc., when the power of L dividing Q to the D minus 1 gets large enough, the decomposition, and L is big enough, the decomposition matrix shouldn't depend so much on L. And then we might as well try to take some limit. And by taking this limit, we are doing something, we're obtaining some new kind of objects that does not depend anymore on this largest power of L dividing Q to the D minus 1. Right, so maybe I should, I want to say the last thing is that from the point of view of decomposition matrices, so if I go back here. So the decomposition matrix for general finite group of Lie type, unipotent part of the representations, involves somehow non-unipotent rows that come from characteristic 0. Characteristic L, everything will be unipotent, but there are things in characters of characteristic 0 characters that are not unipotent playing a role. And as I've explained, this number of rows is somehow not generic. It does depend on a little bit on Q. Specifically, it depends on the largest power of L that divides Q to the D minus 1. So for when you go to the Q-Show algebra, you just get rid of that black rectangle. So what we are doing here is somehow the opposite. We are making the number of rows of that black rectangle go to infinity. Okay. Instead of making this number of rows, which is dependent on the L to the whatever power on the L-adic valuation of Q to the D minus 1, going with that, we are saying, okay, well, let's make that go to infinity, and then it's somehow going to stabilize, and that's what one should consider. Right, so I'll finish the last part of it. So all of that is, I mean, it goes back to all the work with David Craven, and so there's this more recent work with Olivier Dudas, and it's what's underlying that is also the fact that Hilbert schemes have to do with, of points have to do with rational Cherenkov algebras, and rational Cherenkov algebras their category O at certain parameters, that rational parameters are equivalent to modules over Q-Show algebras. So here we have quantized in a different way. We have these Hilbert schemes, and which you can quantize going to the Cherenkov algebra direction. We've quantized in a different direction relating to GL, but the two should be, the two somehow are related. So if you stay at the level of the Hilbert schemes, so we find these two variables polynomials, there's McDonald polynomials and all those combinatorial objects having to do with with double affine algebras, with toroidal Lie algebras. And so what one would like to use, I mean, you can control representations of symmetric groups of Hausdorff algebras at roots of unity using these using two representations of affine Lie algebras of SLP hat or SLD hat. So the hope would be to do for GL or for unitary groups or suitable versions for other finite groups of Lie type is to use not just affine Lie algebra categorification or two representations, but toroidal versions. So what you would need to do is starting with, you would start with a quiver. So a quiver gives you a symmetric Kac-Moody algebra, and then you would have to affinize that. So first, so with your quiver underlying Dynkin diagram, you get bigeneral relations Lie algebra, Kac-Moody algebra. And Lustig explains that you can actually, oops, what's going on with my slides? Sorry, that's well, everything comes at once. So not bad, maybe for the last, that's my last slide. So from this quiver, you get, you can realize the positive part of the quantum group or its enveloping algebra by looking at the modularized stack of representations of that quiver. So you have a big, very big algebraic variety, you quotient by the group, and you use that as a stack. And on that stack, you can look at perverse sheaves. And if you're in the deaking case, that's all. Generally, you take a certain subcategory. So this has a tensor product given by convolution. And the Grottoni group was proven by Lustig to realize the positive part of the Kac-Moody algebra. And simple perverse sheaves correspond to, or even gives you a definition of the canonical basis according to Lustig. And Michele Avagnolo, Eric Weistrow, independently, I checked that this category coincides, this category of perverse sheaves coincides with the category defined by German relations using Quiver-Hager algebras. Okay, so that was my first end of my first slide. So now we would like to affinize this construction. So we can construct a monoidal category. So here's the crucial part, the positive part. So we want to affinize that, take loops in that. So there's definition one can take, at least geometrically. Instead of looking at constructible sheaves or D-modules on our stack, you can look at coherent sheaves on the cotangent bundle. But you have to take the cotangent bundle not as a stack, but as a derived stack. So you can consider this derived stack and look at coherent sheaves on, derived category of coherent sheaves on that. And what Avagnolo and Weistrow have checked is that, so there's ongoing work with them and with Peng Chan on the topic, and what they have done at original, they have checked that the K0 does agree with the quantum affinized positive part of the Kac-Moody algebra. So it's a case, it's a dinking case. It's a case where what you obtain is an affine Lie algebra. G hat is an affine Lie algebra. But now we've used the positive part of that affine Lie algebra in the loop presentation. Okay, so that's really the Drinfeld side of theory. And so when gamma, when the quiver is just a point, so the Lustig theory would realize just a positive part of quantum SL2. And if you look at the cotangent bundle of the space of representations, the space of representations is just disjunction of point modulo GLN, and the cotangent bundle of point modulo GLN is a scheme that, I mean, it's derived the scheme where you take GLN or GLN star, but you put that into -1. So it's an exterior algebra. Functions on it is an exterior algebra. And now you take some stack quotient by dividing by GLN. And you can use causality to relate that to an actual honest stack, where now you take the Lie algebra GLN modulo the group GLN. And Chan, Varinov, Weistrow have proven that this, so this, the derived category of coherent sheaves on that derived stack, or GLN mod GLN is just a stack, should give you a part of categorical version of SL2 hat. Okay, so we start with gamma, has to do with SL2, we've affinized, but we can realize SL2 hat. SL2 hat is a Kac-Moody algebra. We can realize it. We can realize the positive part by using representations of the Kronecker quiver, perverse sheaves and that. And so we have the affine Lie algebra SL2 hat, and there are two ways to get a positive chunk in it. It's either you think of it as a Kac-Moody algebra, or you think of it as a loop algebra. And so what Chan, Varinov, Weistrow have proven is that the part where these two positive things coincide, the categories, the two ways to categorize them coincide. So that relies on a number of equivalences. First of which is the derived Sadake of Finkelberg and Pesokamnikov that relates coherent sheaves on Lie algebra modulo the group to perverse sheaves on the affine Grassmannian, and then you have to do a Radon transform to go to the opposite affine Grassmannian, and then in this case that's vector bundles on it's going to be Perez sheaves on it's Perez sheaves on modular stack on vector bundles of P1 and vector bundles on P1 sits inside coherent sheaves on P1, and coherent sheaves on P1 has a Dirac category equivalent to that of representations of the Kronecker quiver. So that's how you end up there. That's what they show. So there's a question which is the main issue is to try to understand algebraically this construction. Okay, so you can define some monoidal category in a geometrical manner, but it's from the now, even when gamma is just 1 point, it's a trivial case, quiver with no arrows. We don't have a good algebraic understanding of this monoidal category because there's no nice abelian subcategory to work with. Everything is fairly Dirac. But it's probably really good to be able to have a definition of an affinized Kac-Moody algebra monoidal category. That's stop here. Thank you.
Thank you very much, Raphael. Why don't we thank our speaker? Excellent. Yeah, and does anyone have any questions then for Raphael? And please speak up at this point, or I can read your questions as well, of course.
Could you say more about the generalization of your conjecture for the finite unitary groups at d equals 1 to other types?
So it's something, the combinatorics of which we have not yet somehow worked out. So so the way, so I can't say much. So the trick there is to somehow to rely directly on. I mean, there is no Kazhdan-Lustig type complicated combinatorics when d equals when L divides q plus 1. In general, we will need to get started with something that's already somehow of Kazhdan-Lustig combinatoric type or canonical basic type. So that's very much, that's where the when I mentioned stable basis and Maulikov, Bezukhanikov, that's what we start with. So Bezukhanikov tells you structurally, but I mean combinatorially, that's already Maulikov. You have a certain base, you have this Fock space, and there is a certain stable basis, associated to every rational number. So now you would have to take a rational number that so that has denominator d, and to start with that. So the difficulty is to get, you don't get, this stable basis is not defined in one go. I mean, it's defined using some kind of like LLT basis or something like that. Okay, and doing certain combinatorial constructions after. So for the unitary group, for in the general case, we would start with LLT type basis and then apply stable basis things, and then we would do something similar. We would be able to do this. Some of this trick of going from Q to minus Q for the unitary group.
Thanks very much. I think that maybe you answered a different question than I meant to ask. So I'll just ask another question. So if you take G to be a different group, like yes, E8 or something, I mean, what replaces the Hilbert scheme, for example? Like, do you have a different? Do you have Palindromos or spacer?
No, there's no. I mean, this is very speculative. Okay, so but there's you can combinatorially construct something by looking at see one of the characterizations of so McDonald polynomials are very easy to are easy to characterize. They are very hard. What's hard is to prove their existence. So you can use one of the combinatorial characterization of McDonald polynomial. You can make sense of that for other types. So it depends on an order on unipotent characters. But once you have that, you can. There's a unique family if they exist of polynomials for type E8, for example. And then you run the computer, and then, okay, fine, I have a family. And then you define a nabla operator by diagonalizing that, and then you do the same, you do something similar. So that's a way, that's a way things go.
Okay, I see, thanks.
Very well, I will stop the recording now. So if anybody has any questions, please feel free to